Hey everyone, and welcome back for another deep dive. Today, we are going,
Shrinking down.
shrinking down to the atomic level to explore the world of atomic and molecular structure. Get ready for like a crash course in the basic building blocks of, well,
Of everything?
yeah, basically everything.
Like learning the language of the universe.
Yeah.
You know,
I like that.
once you understand atoms and molecules,
Yeah.
you can really unlock like the secrets of chemistry and see how it shapes our world.
I love that analogy. It's mind-blowing to think that everything we see and touch is made up of these tiny particles. Our source starts off with Dalton's atomic theory,
Huh.
even though it's,
A little old school?
yeah, a bit old school. It's like
Right.
the foundation of
Yeah.
modern chemistry.
It really is. Dalton basically said that everything is made up of these tiny indivisible particles called atoms.
Okay.
Of course, we know now that atoms are actually made up of even smaller particles.
Right,
But his theory was a huge step forward.
right. And those subatomic particles, protons, neutrons, and electrons, are what make each element unique. It's amazing to me that we can identify an element just by knowing how many protons it has.
Yeah.
It's like each element has its own atomic fingerprint.
That's the atomic number,
Uh-huh.
and it's one of the most important concepts in chemistry.
For sure.
For example, carbon always has 6 protons, oxygen always has 8, and so on. No matter what, that number never changes.
Yeah, that makes sense. Otherwise, you'd have a completely different element.
Exactly.
And then there's the mass number, which tells us the total number of protons and neutrons in an atom's nucleus, which brings us to isotopes.
Isotopes are atoms of the same element
Okay.
that have the same number of protons but a different number of neutrons.
Okay.
They're like siblings with slightly different weights.
And it turns out we encounter isotopes every day. Think about carbon dating. Scientists use the ratio of different carbon isotopes to determine the age of ancient artifacts and fossils. It's incredible how these tiny variations in atomic structure can unlock secrets from the past.
It's a great example of how understanding atoms can help us understand the world around us.
Okay, let's shift gears and talk about electrons.
Okay.
These tiny particles are negatively charged and constantly in motion around the atom's nucleus. They might seem small, but they are the real drivers of chemical bonding.
It's all about those valence electrons.
Yeah.
The ones in the outermost energy level.
Oh, okay.
They're like the social butterflies of the atom,
Oh, like that.
interacting with other atoms to form bonds and create molecules.
I love that. So how do these valence electrons create those chemical bonds?
Well, sometimes atoms completely give up or gain electrons, forming ions.
Okay.
When an atom loses an electron, it becomes a positively charged cation.
Mm-hmm.
And when it gains an electron, it becomes a negatively charged anion.
So it's like a game of atomic tug-of-war with electrons being passed back and forth.
Exactly.
Oh, yeah.
And these charged ions are attracted to each other, forming ionic bonds. Think about table salt,
Right.
which is made up of positively charged sodium ions and negatively charged chloride ions held together by those strong electrostatic forces.
That's amazing. Okay, so we've talked about the basics of atoms and how they can become ions. What about where these electrons are actually hanging out within an atom? Our source mentions this outdated model called the Bohr model.
Right. Bohr thought that electrons were orbiting the nucleus in these perfect little circles, kind of like planets around the sun.
Mm-hmm.
But it turns out that the world of electrons is much more complex and, dare I say, much more interesting.
That's where the quantum theory comes in, right?
Exactly.
This is where things start to get really mind-bending.
Instead of fixed orbits, electrons are described as existing in these fuzzy clouds called orbitals,
Okay.
which represent the probability of finding an electron in a particular region of space.
So it's less about knowing exactly where an electron is and more about knowing where it's most likely to be.
Precisely.
Yeah, okay.
And this is where the Heisenberg uncertainty principle comes in. It basically says that we can't know both the location and the momentum of an electron with perfect accuracy.
Oh, wow.
The more we know about one, the less we know about the other.
Okay, so there's a fundamental limit to what we can know about these tiny particles.
Right,
But even with that uncertainty, there's still some order to it all, right?
right. Quantum numbers are a way of describing the probable location and energy of an electron. It's like giving each electron its own unique address within the atom.
And these quantum numbers are pretty important, right? They help us understand how electrons are arranged and how they behave.
Absolutely. They're like the foundation for understanding how atoms interact with each other.
There are 4 main types of quantum numbers,
Okay.
each describing a different aspect of an electron's state.
Let's break them down. First up, the principal quantum number, or
Yeah.
this one tells us the energy level of an electron.
It's like saying what floor an electron is on in an apartment building.
Higher in means higher energy and further away from the nucleus. And guess what? You can use the rows on the periodic table to figure out the principal quantum number for an element's valence electrons.
So if we look at sodium, which is in the third row of the periodic table, we know that its valence electrons are in the third energy level.
Exactly.
That's pretty cool. So what about the shape of these orbitals?
That's where the second quantum number comes in the azimuthal quantum number, or L. It tells us about the shape of an electron's orbital.
Okay.
We use letters to describe these shapes. L's for spherical, P for dumbbell-shaped,
Okay.
and then there are D and F orbitals for more complex shapes that we won't dive into today.
Okay, so the first quantum number tells us the energy level, and the second quantum number tells us the shape of the orbital. What about the third one?
The third quantum number is the magnetic quantum number, or ML. It tells us the orientation of an orbital in space. It's like saying which direction an apartment faces within a building.
So it's getting even more specific now.
Right.
And the fourth quantum number?
That's the spin quantum number, or EMS. It describes the intrinsic angular momentum of an electron.
Okay.
It can either be spin up or spin down, kind of like a tiny spinning top.
Wow. So much information packed into just 4 numbers. It's amazing how we can describe something as tiny as an electron with so much detail.
And here's another crucial principle, the Pauli exclusion principle. It states that no 2 electrons in an atom can have the same set of 4 quantum numbers.
Wow.
Each electron has its own unique address within the atom.
So it's like a cosmic rule that prevents 2 electrons from occupying the same space at the same time.
Exactly. Now let's use these quantum numbers to understand how electrons are arranged within an atom.
Yeah.
This arrangement is called the electron configuration.
And you can use the periodic table as a guide to write electron configurations, right?
Yeah.
It's like a cheat sheet for understanding the structure of atoms.
Got it. As you move across the periodic table, you're essentially filling up those orbitals with electrons, according to the Aufbau principle,
Okay.
which basically says that electrons fill the lowest energy levels first.
But there are some exceptions to this rule, right? Our source mentions chromium and copper as examples.
Right, what's fascinating is that these exceptions actually make sense when you think about stability.
Okay.
Atoms prefer to have half-filled or fully filled subshells
Okay.
because those arrangements are more stable.
So sometimes an electron might jump to a higher energy level to achieve that stability.
Exactly. And these seemingly small variations can have big impacts on the chemical behavior of elements.
Okay, so the periodic table is like a roadmap for understanding electron configurations, but things can get pretty complicated when you're dealing with larger atoms.
That's where noble gas configurations come in handy.
Okay.
They let you abbreviate the electron configuration by using the symbol of the previous noble gas.
So instead of writing out the entire configuration for calcium, which would be super long, we can just write RR force 2.
Exactly.
Much easier.
And these configurations are more than just shorthand notations. They actually tell us a lot about how elements will behave when they interact with each other.
So electron configurations give us clues about how atoms will form bonds and react with each other.
That's right. It's like a preview of the chemical personality of an element.
Okay, so we've covered the basics of atoms, electrons, and electron configurations. Are we ready to talk about how these atoms get together to form molecules?
Let's bond. Welcome back to our atomic adventure.
We're about to level up our understanding of molecules
Oh, yeah.
with Lewis dot structures. They're like blueprints
All right.
that show us how atoms are connected
Yeah.
and where those crucial valence electrons are hanging out.
They're a fantastic visual tool for understanding like the architecture of molecules.
So how do we actually draw these Lewis structures?
First, you need to figure out how many valence electrons each atom has. Remember, those are the electrons in the outermost shell,
Right.
the ones responsible for forming bonds.
Right. And we can use our trusty periodic table to figure that out, right?
Absolutely. Each column or group on the periodic table tells us the number of valence electrons for the elements in that group.
It's like the periodic table is a built-in cheat sheet for chemistry.
It is.
Okay, so once we know how many valence electrons we're working with, what's next?
Then you arrange the atoms,
Okay.
usually putting the least electronegative atom in the center,
Okay.
unless it's hydrogen, which always goes on the outside.
Makes sense. And then we connect those atoms with single bonds,
Yes.
which represent 2 shared electrons.
Exactly. And then comes the fun part, filling in those octets.
Ah, yes, the octet rule. Our source mentions that most atoms want to have 8 electrons in their valence shell to achieve stability.
It's like they're trying to reach a state of Zen. A full outer shell of 8 electrons makes them feel happy and stable.
Okay.
Of course, there are always exceptions in chemistry.
Of course.
Right.
Our source mentions that some elements, like hydrogen and helium, are content with just 2 electrons.
Right, they have a smaller valence shell and are happy with a duet of electrons instead of a full octet.
And then there are some elements that can actually handle more than 8 electrons.
Those are the elements in the third row of the periodic table and beyond.
Okay.
They have access to d orbitals, which are like extra storage space for electrons, allowing them to have expanded octets.
So it's like they have a bigger house to accommodate more electrons.
Yeah.
Our source gives the example of sulfur tetrafluoride, SF4,
Right.
where sulfur ends up with 10 electrons around it.
Exactly. Those extra electrons go into sulfur's d orbitals,
Okay.
allowing it to exceed the octet and form more bonds.
Okay, so let's try drawing a Lewis structure. Our source uses ammonia, NH3, as an example.
Perfect. Nitrogen is less electronegative than hydrogen, so it goes in the center. Nitrogen has 5 valence electrons, and each hydrogen has 1, giving us a total of 8 valence electrons to work with.
Then we connect the nitrogen to each hydrogen with a single bond,
Right.
using up 6 of those electrons.
Right. And the remaining 2 electrons go on nitrogen as a lone pair, giving it a full octet. Each hydrogen is also happy because it's sharing 2 electrons with nitrogen.
Perfect. Our Lewis structure for ammonia is complete. What happens if a molecule has an odd number of valence electrons?
That's a great question. In those cases, it's impossible for every atom to have a full octation. One atom will end up with an unpaired electron.
Our source gives the example of nitric oxide, NO, which has 11 valence electrons.
Right. No matter how you arrange the electrons, one of the atoms will be short of a full octet.
Okay, so there are always those little exceptions that keep things interesting. Are there any shortcuts for drawing Lewis structures?
Absolutely. If you have a molecule with hydrogen or halogen atoms,
Okay.
you can simplify things a bit.
How so?
Well, hydrogen can only form one bond,
Right.
and halogens usually form one bond to complete their octet.
Okay.
So you can automatically place them as outer atoms and just draw a single bond connecting them to the central atom.
That's super helpful. It saves us a few steps.
Exactly. But sometimes, even with those shortcuts, you might run into situations where you can draw multiple possible Lewis structures for the same molecule.
That's where formal charges come in, right?
Yeah, you got it.
They help us decide which Lewis structure is the most likely or most stable.
Formal charges are like a way of checking to see which structure is the most electronically balanced.
So how do we calculate these formal charges?
Our source provides a handy formula.
Okay.
Formal charge, number of valence electrons, number of non-bonding electrons, number of bonds.
Okay, so we're basically comparing how many valence electrons an atom owns in the Lewis structure to how many it would have in its neutral state.
Exactly. And the idea is that the most stable Lewis structure will have formal charges that are as close to 0 as possible.
Our source uses carbon dioxide, CO2, as an example.
Okay.
One possible Lewis structure gives oxygen a formal charge of -1 and carbon a formal charge of +2. But a more stable structure gives all 3 atoms a formal charge of 0.
So that second structure is the preferred one because it's more balanced in terms of electron distribution.
Precisely. It's all about finding the arrangement of electrons that gives the molecule the lowest energy and greatest stability. Okay, so we've got Lewis dot structures down. Are we ready to go even deeper into the world of bonding?
Let's dive into molecular orbital theory. This theory takes a more sophisticated look at how those atomic orbitals combine to form molecular orbitals.
Sounds intriguing, but also a little intimidating.
Don't worry, it's not as complicated as it sounds.
Yeah.
The basic idea is that when atoms form covalent bonds, their atomic orbitals overlap, creating these new molecular orbitals.
Our source uses the simple example of a hydrogen molecule, H2.
Right. The one's orbitals of the 2 hydrogen atoms overlap, forming a molecular orbital called a sigma bond.
Okay.
This sigma bond is lower in energy than the original atomic orbitals, which explains why the H2 molecule is more stable than 2 separate hydrogen atoms.
So by sharing electrons in this sigma bond, the hydrogen atoms achieve a lower energy state and become more stable.
Exactly. It's all about achieving that energetic zen.
Yeah.
Now, our source also points out that you don't always need to combine the same types of atomic orbitals to form a bond.
So it's not always a perfect match?
Not necessarily. For example, in hydrogen fluoride, HF,
Okay.
the 1's orbital of hydrogen overlaps with a 2p orbital of fluorine to form the bond.
Interesting. So different types of orbitals can overlap as long as they can effectively share electrons.
Precisely. And this leads us to the fascinating concept of hybridization.
I've heard of this. It's like atoms mix and match their orbitals to create these hybrid orbitals that are better suited for bonding.
That's a great way to put it. Hybridization helps explain why molecules have the shapes they do and why we sometimes see those unexpected bonding patterns.
Our source focuses on carbon as a prime example of hybridization.
Yeah,
And for good reason, carbon is incredibly versatile when it comes to bonding, forming the backbone of all sorts of organic molecules.
right. Carbon can undergo sp3, sp2, or sp hybridization,
Okay.
depending on how many atoms it's bonding with.
Okay, let's start with sp3 hybridization.
This is the type of hybridization we see in methane, CH4,
Okay.
where carbon forms 4 single bonds with 4 hydrogen atoms.
But wait, if we look at carbon's electron configuration, it only has 2 unpaired electrons in its 2p orbitals. How does it form 4 bonds?
That's the beauty of hybridization. One of carbon's 2's electrons gets promoted to the empty 2p orbital, giving it 4 unpaired electrons.
So it's like carbon is rearranging its electrons to maximize its bonding potential.
Exactly. But there's another step. Those 4 orbitals, the 2's and the 3 2p orbitals, actually combine to form 4 identical hybrid orbitals,
Okay.
called sp3 orbitals.
So carbon blends those orbitals together to create these new superbonding orbitals.
That's a great way to visualize it. These sp3 orbitals are all equivalent in energy and have a shape that allows for optimal overlap with other atoms.
Our source even mentions that the way these sp3 orbitals are arranged gives methane its tetrahedral shape.
Exactly. The 4 sp3 orbitals point towards the corners of a tetrahedron, maximizing the distance between them and minimizing electron repulsion.
Okay, so that's sp3 hybridization. What about sp2?
In sp2 hybridization, carbon combines 3 of its orbitals,
Okay.
the 2's and 2 of the 2p orbitals. This leaves 1 unhybridized p orbital.
And this is what we see in molecules like ethene, C2H4,
Yes.
where carbon forms a double bond.
Right. The 3 sp2 orbitals form 3 sigma bonds,
Okay.
one with each hydrogen and one with the other carbon atom.
And those sigma bonds are formed by direct head-to-head overlap of orbitals, right?
Exactly. Now, what about that leftover p orbital? It forms a pi bond with the unhybridized p orbital on the other carbon atom.
And pi bonds are formed by sideways overlap of those p orbitals.
You got it. So in ethene, each carbon has 3 sigma bonds and 1 pi bond,
Oh.
giving it a total of 4 bonds.
Our source points out that the combination of a sigma and pi bond in a double bond actually restricts rotation.
That's an important point.
Okay.
Unlike sigma bonds, which allow free rotation, pi bonds lock those atoms in place.
Okay, so sp3 gives us 4 sigma bonds and a tetrahedral shape.
Right.
sp2 gives us 3 sigma bonds and 1 pi bond with a planar shape. What about spi hybridization?
With bihybridization, carbon combines only 2 of its orbitals,
Okay.
the 2's orbital and one of the 2p orbitals. This leaves 2 unhybridized p orbitals.
And this is what we see in molecules like ethene, C2H2,
Right.
where carbon forms a triple bond.
Exactly. The 2 square orbitals form 2 sigma bonds,
Yeah.
one with a hydrogen atom and one with the other carbon atom.
And those 2 leftover p orbitals.
They form 2 pi bonds with the unhybridized p orbitals on the other carbon. So in ethene, each carbon has 2 sigma bonds and 2 pi bonds,
Okay.
giving it a total of 4 bonds.
Wow. So carbon can customize its hybridization depending on how many bonds it needs to form.
That's right. And there's a handy way to predict the hybridization of an atom just by looking at its structure.
Tell me more.
You can count the number of electron domains around an atom. An electron domain is any region where electrons are concentrated,
Okay.
whether it's a lone pair or a bond.
So in methane, CH4, carbon has 4 electron domains because it has 4 single bonds.
Exactly. And since it needs 4 orbitals to accommodate those 4 electron domains,
Right.
it undergoes sp3 hybridization.
Okay, that makes sense. What about ethene, C2H4?
Each carbon in ethene has 3 electron domains,
Okay.
2 single bonds and 1 double bond. Remember, double and triple bonds count as 1 electron domain.
So it undergoes sp2 hybridization because it needs 3 hybrid orbitals.
You got it. And in ethene, C2H2, each carbon has 2 electron domains,
Okay.
1 single bond and 1 triple bond.
Okay.
So it undergoes sp hybridization because it needs 2 hybrid orbitals.
So the number of electron domains gives us a clue about the hybridization of an atom. That's a really helpful trick.
It is. It helps connect those electron configurations to the actual shapes of molecules.
Okay, I'm ready for the next level of visualization. What about molecular orbital diagrams?
Molecular orbital diagrams are a way of visualizing how those atomic orbitals combine to form molecular orbitals. which, as we've discussed, is the basis for covalent bonding.
Our source uses oxygen, O2, as an example to illustrate how to draw a molecular orbital diagram.
Right. We start by listing the valence atomic orbitals of the two oxygen atoms side by side.
Okay.
Then we show how they combine to form molecular orbitals, with bonding orbitals lower in energy and antibonding orbitals higher in energy.
And then we fill those molecular orbitals with electrons,
Yes,
starting with the lowest energy levels and following Hund's rule, which tells us to fill those orbitals singly before pairing up electrons.
exactly. And once we have the molecular orbital diagram, we can use it to calculate the bond order of the molecule.
Which tells us how many bonds there are between the atoms.
Right. The bond order is calculated by subtracting the number of electrons in antibonding orbitals from the number of electrons in bonding orbitals and dividing by 2,
So for oxygen, we have 8 electrons in bonding orbitals and 4 in antibonding orbitals, giving us a bond order of 8 to 4, 2 equals 2.
which means oxygen have a double bond, just like we saw in its Lewis structure.
It's so cool how these different models connect and support each other.
You really do. And molecular orbital diagrams can also tell us whether a molecule is paramagnetic or diamagnetic.
Refresh my memory, paramagnetic means it has unpaired electrons and is attracted to a magnetic field, right?
Exactly. And diamagnetic means all its electrons are paired up, so it's not attracted to a magnetic field.
Our source shows us that oxygen is paramagnetic because it has 2 unpaired electrons in its molecular orbital diagram.
Right. And nitrogen, N2, on the other hand, is diamagnetic because all of its electrons are paired.
So molecular orbital diagrams are pretty powerful. They give us information about bond order, magnetism, and even bond strength.
Speaking of bond strength, our source highlights some of the key factors that influence how strong a bond is.
Bond order is one of the big ones, right?
Absolutely.
A triple bond is stronger than a double bond, which is stronger than a single bond.
Absolutely. More shared electrons mean a stronger attraction and a more stable bond.
And atomic size also plays a role.
It does. Smaller atoms can get closer together, leading to greater overlap of their orbitals and a stronger bond.
And what about electronegativity?
Electronegativity is definitely a factor. A larger difference in electronegativity between two atoms typically leads to a stronger bond,
Okay.
because the more electronegative atom pulls those electrons closer, creating a stronger attraction.
Our source also mentions that lone pairs can actually weaken bonds.
That's because lone pairs take up more space around an atom,
Okay.
increasing repulsion between electron pairs and weakening the bond.
Okay, so we've explored molecular orbitals and the factors that affect bond strength. What's next on our journey into the molecular world?
Let's move from 2D to 3D and explore the fascinating world of molecular geometry, the shapes of molecules.
3D molecules. Sounds complicated.
Don't worry, we have a great tool to guide us, the valence shell electron pair repulsion, VSEPR theory.
Okay, I'm ready to get geometric. What's the basic idea behind this VSEPR theory?
The VSEPR theory basically states that electron pairs around a central atom will arrange themselves to be as far apart from each other as possible.
Makes sense. Electrons are all negatively charged, so they're going to want to spread out and avoid each other as much as possible.
Exactly. It's like they need their personal space. And this simple idea can be used to explain the shapes of so many different molecules.
Our source describes the 5 main electron domain geometries: linear, trigonal planar, tetrahedral, trigonal, bipyramidal, and octahedral.
Let's start with linear,
Okay.
the simplest geometry, where you have 2 electron domains around the central atom.
A great example is carbon dioxide, CO2. The 2 oxygen atoms are on opposite sides of the carbon atom,
Right, yeah.
forming a straight line.
And the bond angle in a linear molecule is 180 degrees.
What about trigonal planar?
With trigonal planar geometry, you have 3 electron domains around the central atom,
Okay.
all in the same plane.
Like boron trifluoride, BF3. The 3 fluorine atoms are arranged around the boron atom like the points of a triangle.
And the bond angles in a trigonal planar molecule are 120 degrees. So far, so good.
So far, so good. Okay, what about tetrahedral?
Tetrahedral is a common geometry for molecules with 4 electron domains around the central atom.
Like methane, CH4, the 4 hydrogen atoms are arranged around the carbon atom like the corners of a tetrahedron.
Right, and the bond angles in a tetrahedral molecule are 109.5 degrees.
Okay, those geometries make sense. What about those more complex ones, trigonal, bipyramidal, and octahedral?
Trigonal bipyramidal has 5 electron domains around the central atom
Okay.
and kind of resembles 2 pyramids joined at their bases.
Our source uses phosphorus pentafluoride, PF5, as an example. 5 fluorine atoms surrounding that central phosphorus atom.
Exactly. And octahedral, you guessed it, has 6 electron domains around the central atom.
Okay.
They're arranged like the corners of an octahedron, which is basically 2 square pyramids joined at their bases.
Our source gives the example of sulfur hexafluoride, SF6. 6 fluorine atoms, all perfectly spaced around the sulfur atom. Okay, so those are the 5 main geometries. But what about those lone pairs we talked about earlier? Do they affect the overall shape of a molecule?
They absolutely do. Lone pairs actually exert a stronger repulsive force than bonding pairs,
Why is that?
because lone pairs are held closer to the nucleus than bonding pairs.
Okay.
They take up more space and push those bonding pairs closer together.
So it's like they're demanding a bit more personal space.
Exactly. And this can distort the bond angles and change the overall shape of the molecule.
Our source uses water, H2O, as an example.
Water is a great example. Oxygen in water has 4 electron domains,
Okay.
2 lone pairs and 2 bonding pairs. If it were just the bonding pairs, the molecule would be linear,
Okay.
with the hydrogen atoms on opposite sides of the oxygen atom.
But those lone pairs push the hydrogen atoms closer together,
Right.
giving water its characteristic bent or V shape.
Exactly. And the bond angle in water is actually less than 109.5 degrees because of those repulsive lone pairs.
So those lone pairs are like little molecular architects shaping the molecule. Okay, it seems like those lone pairs can definitely make things more complicated, but it's all about finding that arrangement that minimizes repulsions.
Right. And luckily, our source has a really helpful table summarizing all the different molecular geometries, taking into account both bonding pairs and lone pairs.
It's like a molecular shape cheat sheet. Now, once we know the molecular geometry, can we determine the overall polarity of a molecule?
That's a great question. We talked about bond polarity earlier, but now we're thinking about the polarity of the entire molecule.
And this depends on both the polarity of the individual bonds and the overall shape of the molecule.
You got it.
Okay.
Our source gives us a good example, carbon tetrafluoride, CF4.
Okay.
Each CF bond is polar because fluorine is more electronegative than carbon.
Right.
But because those 4 bonds are arranged symmetrically around that central carbon atom,
Okay.
the dipoles actually cancel each other out.
Right. So even though it has polar bonds, the molecule itself is nonpolar.
Exactly. Symmetry is key here. If the molecule is symmetrical and those bond dipoles are equal and opposite,
Okay.
they'll cancel each other out, resulting in a nonpolar molecule.
But if the molecule is asymmetrical, or if those bond dipoles are unequal, then the molecule will be polar.
Precisely. Our source uses dichloromethane, CH2Cl2, as an example of an asymmetrical polar molecule.
Okay, I see. So it's not just about whether the bonds are polar, it's about how those bond dipoles are arranged in space. That makes a lot of sense.
It does. And this concept of molecular polarity is incredibly important because it affects how molecules interact with each other and explains many of their physical and chemical properties. Okay, so we've gone from the structure of atoms to the shapes of molecules. We've covered a lot of ground.
It's amazing to think that we started with tiny particles like protons and neutrons, and now we're talking about these 3D shapes of molecules.
It really is a testament to the power of, like these fundamental concepts.
Yeah, for sure. We've covered so much ground in this deep dive, from atoms and bonding to molecular geometry.
Yeah, it's been quite a journey through the molecular world.
So as we wrap up this exploration of atomic and molecular structure, what are some of the key takeaways you'd like to leave our listeners with?
Well, I think the biggest takeaway is to appreciate the elegance and complexity of the atom.
Okay.
These tiny particles with their protons, neutrons, and electrons are the building blocks of everything around us.
It's incredible to think that everything we see, touch, and interact with is made up of these tiny particles.
It really is.
Yeah.
And it's those electrons,
Yeah.
these negatively charged particles that really drive the show when it comes to chemistry.
Mm.
Their arrangement in atoms determines how atoms bond together, the shapes those molecules will have, and ultimately how those molecules behave in the world.
We've seen how those seemingly simple concepts of electron configuration, hybridization, and VSEPR theory can explain so much about the diversity of molecules.
Absolutely. And these models, these ways of visualizing and understanding molecular structure, are powerful tools for predicting and explaining the properties of matter.
It's mind-blowing to think that everything from the strength of steel to the fluidity of water comes down to the interactions between those tiny particles.
It really does. Now that you have a grasp of the basics of atomic and molecular structure, think about this. How do the principles we've discussed explain the properties of materials you encounter every day, from the flexibility of plastic to the conductivity of metals?
It's like a whole new world has opened up just by understanding those fundamental principles.
Exactly. And I encourage you to keep exploring, keep asking questions.
Well said. It's been an incredible journey. Thanks for joining us on this deep dive into atomic and molecular structure. We'll see you next time for another fascinating exploration.